Hey folks, Dr. Phil here. So this is going to be a video on Chapter 12, Analysis of Variance, what we sometimes call ANOVA in statistical circles. So a one-way ANOVA is the first one we'll talk about. This is used to compare three or more treatment means. The assumptions underlying ANOVA are, when we say assumptions, these are the things that really we have to assume, and there are some ways we can test for these things to make sure this test will be robust. So the underlying assumptions for ANOVA are the samples are from populations that follow normal distribution. So think of the bell curve. The populations have equal standard deviations, and the populations are independent, so they're not related to each other. When the conditions are met, the test statistic has an F distribution. So why do we need ANOVA? Why not just use the previous method based on the T distribution? So we could compare the population means two at a time. We could certainly do that. Let's look at an example. Let's say we got four groups, and there are six comparisons we can make. We can make each comparison at the 95% level. So think about the alpha, the 0.05 significance level. So the probability that all are correct, so the 0.95 times 6 would be equal to 0.735. So the probability of at least one error is then, of course, 2.265, right? 1 minus the 0.735. So the type 1 error buildup is not satisfactory because every time you just add them, you lump them all together, you're you're basically increasing the potential for the type 1 error. So ANOVA allows us to compare all the means simultaneously, and if that also avoids this problem here of this type 1 error buildup. So let's take a look at a quick example. So Joyce Coleman manages a regional financial center. She wants to compare the productivity as measured by the number of customers served among three employees. So you can see them here, Wolf, White, and Carosa. 4 days are randomly selected, and the number of customers served by each employee is recorded. So the question is there a difference in the mean number of customers served? So let's continue. So we can see here we've got the employee, we've got the customers served, we've got the mean for Carosa, the mean for Wolf, and the mean for White, right? So this is, if you think about what these differences are here, this is basically different versus not different, right? So this is what's that speaking to? Null hypothesis relative to research hypothesis. So we want to determine if the population means are different. So we assume the population variances are the same. So ANOVA compares means through their variances. So we estimate the common population variances in really one of two ways. The test statistic is the ratio of the two estimates that you're about to see. So first one, if the means are the same, the ratio should be 1. Makes sense, right? If the ratio is larger than 1, we might conclude the means are not the same. So we can use the F distribution to determine when the ratio being greater than 1 occurred by chance. So what we're going to do is we're going to take this total variation and we're going to break it down into two parts. So the total variation is the sum of the squared differences between each observation and the overall mean. And then we're going to break it down as so you see here the treatment variation, the sum of the squared differences between each treatment mean and the grand or overall mean. And then the random variation, that's more of the systematic kind of variation, the sum of the squared differences between each observation and its treatment mean. So the test statistic, the F statistic is basically just the ratio of those two. So as it says, F equals between treatments estimate divided by within treatments estimate. Okay, so we're assuming it'll have an F distribution, almost always does. The numerator, degrees of freedom, is going to equal K minus 1. You've heard me talk in previous videos about sometimes students will say like, why do they minus 1? It just really makes the numbers a little more conservative, a little more robust by taking 1 out of the sample. So our denominator, degrees of freedom, is going to equal n minus k, and k is the number of treatments, and then n is the total number of observations. So our SS, that all you've seen this before, sum of squares total. So we have basically the sum of the differences between x minus the mean squared, and then SSE is sum of the squared errors. So within, we're saying basically SST equals the SS total from up here minus the SSE here. Okay, and then x bar sub g is, as it says, is the overall grand mean, and then x bar sub c is the sample mean for treatment C. And we can summarize this with an ANOVA table thusly. So we got the source of variation, treatment error, and the total. We've got the sum of squares, as we just talked about, SST, SSE, and then SS total. We have our degrees of freedom, k minus 1 for the treatments, n minus k for the error, and then n minus 1 for total. And then we can see our mean square. This is what we just talked about above. And then we have our f. Really, all you need to take away from this is that to calculate f, we basically have MST over MSE. So let's look at an example. So a group of 4 airlines hired Brunner Marketing Research Inc. to survey passengers regarding their level of satisfaction with a recent flight. 25 questions offered a range of possible answers. So excellent 4, good 3, fair 2, and poor 1. So the highest possible score was 100. So we've got the four airlines here. So the question is there a difference in the mean satisfaction level among the 4 airlines? So step 1, I'm just writing out my null hypothesis. Basically, that there is, again, remember a null hypothesis is there's no change, right? So they're all the same, they all equal each other. And then our research or alternative hypothesis, we're just saying the mean scores are not all equal. Well, step 2, we got what significance level are we using? 0.01, so basically 10% alpha, 10% significance level. And then step 3, F, as we remember, we just did that. If we go back real quick, right here, F is MST over MSE, mean of the squared errors. So for step 4, we have K equals 4, and then we have N equals 22. Now remember, K, if I go back real quick, K is what? K is the degrees of freedom. Okay, so it was K minus 1 and then N minus K. So if we go back, you can see where I plugged that in here. So K minus 1 equals 4 minus 1, which is 3. And then the denominator degrees of freedom, N minus K, which is 22 minus 4. And that gives us the 18. So the critical value is thus 5.09. So you can see here, I just included some of the outputs here so you can see it. So our sum of squares total equals 1,485.10. You can see some of the output here. We can see our grand mean, which is that. Remember that was that. If I go back real quick, go back to yeah. Remember this X bar sub G. That's what they're talking about. That's the overall grand mean. And then you can kind of see here what these are basically the variances from the mean. And then we have our sum of squares total here, which of course is the 1,485.10. Step 5. Now we're going to do the sum of the squared errors. So we plug in all our numbers, the variances, they're all relative to the grand mean, they're squared, and we get 594.41. Again, just to show you would do that on the computer. I'll put that in there for you too. So we get 594.41. So then we take our SST, which is our SS total, which was that 1,485.10, excuse me. And then we subtract the SSE, sum of the squared errors, 594, and we get 890.69. All right, step 5. So we have the MST, which is equal to the SST over K minus 1. So again, I know some of this probably looks a little intimidating. Don't be intimidated by it. I promise you, it's just a case of plugging your numbers. That's all you got to do. So for MST equals SST, K minus 1, we get 296.90. Then we get 33.02. And then for F, we get 8.99. And then I can kind of plug these numbers in down here, as you see, 296.90. There's my 33.02. And then there is my 8.99 for F. So what I know is that the test statistic is greater than the critical value. So what can I do? If it's anytime it's greater than, I can what? I can reject the null hypothesis. Thus, I'm saying I'm basically indirectly saying I can accept my research hypothesis. So what can we do? We can conclude population means are not all equal. Now, what about a two-way analysis of variance? That was a little bit about a one-way analysis. What if you want to do a two-way analysis of variance? So we've only considered one source of variation, right? Total equals between and within. That's just what we did, right? Think about the numerator and the denominator. We called the within error the error or random variation, but there might be other sources of variation that we may also want to try to explain. If we can explain more of the variation, then there's less error or random variation because there's less left over, right? So, denominator of the F statistic would then, of course, be smaller. Results in a larger F statistic typically. We might reject. We might. I put we might reject the null hypothesis because it doesn't mean we definitely will. You can never say you definitely will or won't. That's why you do the test, right? And we refer to any other variables as what we call in statistics blocking variables. So let's take a look at those. So, blocking variable. A second treatment variable that when included in the ANOVA analysis will have the effect of reducing the SSE term. And you can see down here, I've got the source of variation, treatment, blocks, error, and total. Excuse me, I've got my sum of squares. And now the only difference here is I've added in the blocks. So I've just labeled that SSB, sum of the squared blocks. And then I'm going to say block at B minus 1 for degrees of freedom. And then if you look at, if you look at these formulas, right, they're not exactly that much different, right? Look at these two, K minus 1. Now I'm just saying B minus 1, right? And then I'm going to generate an F score for this value as well. So let's take a look at an example of how this works. So water is expanding bus service from the suburb of Starbrick to the business district of Warren. So there are 4 routes being considered and 5 drivers. So we have the driver names here, Dean, Snavely, Ormson, Zalako, and Philbeck, it looks like. And then we have the 4 routes here. And then we've got the number of, presumably the number of minutes. We would hope this wasn't hours, right? This would be the number of minutes it would take to get there. So at the 0.05 significance level, so think about the alpha of 5%. Is there a difference in the mean travel time along the 4 routes? And if we remove the effects of the drivers, so think about the drivers as maybe that blocking variable. Is there a difference in the mean travel time? So, a little bit of output here for you. So you can see I plugged the numbers in, I generated an F. This is done in Excel, by the way. You can do all this very easily in Excel. Nobody's expecting you to write out these formulas. And if you want to solve them by hand, you're welcome to do that. No one in the real world is doing that. Most of us are just using programs like SPSS, Starter, R, Python. There are elements of Python you can use for that. But this is just Excel, right? 2.483. So you can see our between groups, and then you can see the within groups. So this is kind of the treatment is speaking to the between groups, sum squared, and then the error within groups, this 156.4, representing that error that's present within groups. That's more like that systematic variance, if you will. All right, so as always, I write out my null hypothesis, right? H sub 0, that's always null hypothesis, and these are all equal because I'm saying in a null hypothesis there's no change, right? And then H1, my research hypothesis, not all travel time means are the same. So the p-value is 0.098. If you can see, it's right next to the one that's highlighted, the F value. Look over to the right. The p-value is 0.098, so do not reject the null hypothesis. Differences in the mean travel time due to route could just be due to chance. Now, if this was less than 0.05, you see how it's 0.098, so that's like, think about like 9.8%. But our cutoff value was 5%. Let's say that had been less than 5%, then we would reject the null hypothesis. So let's let drivers, as I said, let's let drivers be the blocking variable, right? So you can see our drivers over here on the left, and then you can see our full routes, and we've got the time in minutes. And then we've got, if you look down here, what do we got? We've again got the 5 drivers. We've got the travel time from Starbrick to Warren. We've got the travel time from Starbrick to Warren to West End, and then to West End. And then you can kind of see how this is changing, right? If we got the driver sums in these far 2 right columns. So you can see what I've done here to the ANOVA. I added in basically the blocking variable, if you will. And you can see look at the F value. I got a 9.785. And look at the p-value now. Remember how before it was, if I go back real quick, it was 0.098, right? If we're accounting for the blocking variable, my F has gone up and my p-value is now 0.0001, right? So my hypothesis, the null is the same as before. We're just saying everything is equal to each other. My H sub 1, same as before, right? Not all travel times means are the same because this is the inequality. P-value is 0.004. So now what can we do? We can reject the null hypothesis. So now, because we took into account that blocking variable, we can conclude there is a difference in the mean travel times for the different routes. So if you didn't think of it like this, if you didn't factor in the drivers, you would have potentially reached an erroneous conclusion. All right. Thanks for watching this video, and as always, I will see you in a future video.